Concrete is a highly rigid material, locked in a permanent state of war with its environment. It has immense compressive strength to support multi-ton loads, but that same stiffness makes it vulnerable. A poured slab is constantly subjected to three primary vectors of environmental stress: massive temperature gradients between day and night, deep variations in seasonal moisture, and the relentless frictional restraint of the subgrade dragging against the bottom of the concrete as it tries to move. Left to its own devices, a continuous concrete slab cannot absorb these forces. It will inevitably relieve the built-up internal stress through random, catastrophic fracturing. The core philosophy of pavement engineering is not to try and stop concrete from breaking. That is physically impossible. Instead, we dictate exactly where and how it breaks. Structural pavement design is the art of managing planned weaknesses to preserve the overall integrity of the highway. In India, the definitive rulebook for this process is IS 6509. It is a structural equilibrium matrix that codifies these engineered discontinuities into specific functional units we call joints. These joints are calculated to accommodate three distinct movements: longitudinal expansion when the concrete heats up, longitudinal contraction when it cools, and the angular warping that occurs when the top of the slab is a different temperature than the bottom. This creates a central engineering paradox. The pavement must be physically severed to relieve thermal stress, but at the exact same time, it must remain structurally connected to transfer heavy traffic loads across the gap without differential settlement. Resolving this contradiction requires a precise combination of joint geometry and specialized steel embedments across the cut. A durable highway is achieved by categorizing physical forces and isolating them with highly specific, mechanically distinct joint types. We begin with transverse expansion joints. These are full-depth physical breaks running perpendicular to the flow of traffic, outfitted with a compressible joint filler. This cross-section shows the mechanical purpose of the expansion joint. During peak summer temperatures, the slabs absorb heat and expand horizontally. The gap gives them room to grow, preventing the slabs from colliding and blowing out upward under the pressure. The engineering rule for this filler is strict. The gap thickness provided must be at least twice the maximum estimated expansion of the concrete. This ensures the filler material itself is never compressed to more than 50% of its original size, maintaining its elasticity. To counter the opposite forces, dropping temperatures and the natural shrinkage of curing concrete, engineers deploy transverse contraction joints, often called dummy grooves. By cutting a groove only 1/3 to 1/4 of the way into the pavement depth, engineers create an artificial stress concentrator. When the concrete inevitably shrinks and tears, the crack is forced to propagate straight down from the tip of the cut, neatly hiding the fracture beneath the surface. Transverse joints handle the dominant longitudinal shape changes of the highway, dictating the safe geometric boundaries of the slab. But cutting these joints introduces the load transfer problem. Severing the structural connection means a passing truck tire will press one slab down while the adjacent slab stays high, destroying the foundation beneath the gap over time. The solution is the dowel bar, the essential steel embedment for load transfer across transverse joints. The critical physical property of the dowel bar is that it must be perfectly smooth and unbonded to the concrete on one side. This allows the slab to slip horizontally along the bar during thermal expansion, while the rigid steel transfers vertical shear forces evenly across the gap. However, there is a strict structural limitation defined in IS 6509 Table 2. Dowel bars are mathematically ineffective and strictly prohibited in any slab less than 150 millimeters thick. The surrounding concrete simply lacks the mass to hold the steel under shear stress. This horizontal sliding action sits in stark contrast to longitudinal warping joints, which run parallel to the center line to separate the traffic lanes. Longitudinal joints require a completely different embedment, the tie bar. Unlike dowels, tie bars use deformed, ribbed steel that is fully bonded to both slabs. Their mechanical function is the exact opposite, gripping the concrete in tension to prevent the adjacent lanes from drifting apart. Tie bars must maintain a delicate balance. They hold the slabs together horizontally, but their diameter must be restricted to under 20 millimeters. They need to remain flexible enough to bend slightly when the surface heats up and causes the slabs to warp angularly at the edges. The mechanical dichotomy is clear. Transverse dowels must slip to absorb expansion, while longitudinal tie bars must grip to prevent lateral drift. With the micromechanics established, We apply these rules to the macro layout of the highway grid, dictated by the spacing matrix in Table 1 of the code. For standard plain cement concrete pavements, joint frequency is largely a function of foundation friction. This matrix shows how a rough subbase grips the concrete tightly as it tries to shrink. To prevent the slab from tearing itself apart mid-span, contraction joints must be spaced very closely, at a maximum of 4.5 meters. A smoother foundation generates less friction, safely allowing wider slab spacing. But advanced pavement designs alter this mathematical equilibrium. Take continuously reinforced concrete pavements with elastic joints, or CRC-EJ. In this system, the longitudinal steel is not cut at the contraction joint. Instead, the rebar is painted with a bond-breaking layer for a short distance on either side of the gap. This forms an elastic joint, allowing the steel to stretch slightly under tension and distribute stress without snapping. By utilizing these elastic joints, CRC-EJ pavements entirely eliminate the need for internal expansion gaps within a continuous section. Pre-stressed concrete, or PSC pavements, rewrite the rules even further. By running high-tensile steel cables through the slab and pulling them tight, PSC creates extreme internal compression. This compression overrides the natural thermal expansion forces, allowing for massive continuous slabs of up to 140 meters in length, punctuated only by specialized steel plate expansion joints at the extreme ends. The dimensions in Table 1 are not arbitrary limits. They are a calculated equilibrium, balancing the concrete type, the internal reinforcement strategy, and subgrade frictional drag. Translating this theoretical perfection into reality requires extreme precision on the job site against the sheer physical weight of curing concrete. A millimeter of error in dowel placement carries catastrophic risk. If smooth bars aren't perfectly parallel to the center line, they act as anchors. They lock the joint, prevent thermal slip, and shatter the concrete from the inside out. To prevent this, contractors use rigid hardwood bulkheads or deep metal channel covers to physically lock the dowel bars in perfect parallel alignment, resisting the violent dislodging forces of the internal vibrators during the concrete pour. The execution of the dummy groove contraction joint operates under equally strict timing constraints. When using a concrete saw to cut the groove, the operation must occur in a narrow window, exactly between 12 and 18 hours after the concrete is poured. Cut too early, and the wet concrete simply flows back into the groove, sealing the cut. Cut too late, and the massive thermal contraction stresses of the curing process will have already formed random microcracks throughout the slab. The structural mechanics of a joint are entirely dependent on geometric precision and strict temporal execution before the concrete achieves full set. Fast forward to the highway's operational lifespan. The slab's physical defense is entirely handed over to the joint sealing compound holding the surface line. The compound's sole job is preventing the ingress of water and foreign matter into the gap, but it degrades relentlessly under heavy traffic and ultraviolet exposure. The first mode of failure is shrinkage. The compound pulls away from the concrete faces, turning the joint into a funnel. Surface water channels directly into the subgrade below, eroding the soil and destroying the foundation's load-bearing capacity. The second failure mode occurs when traffic rips the compound out, allowing incompressible stones to wedge into the gap. When summer temperatures return and the slabs expand, those trapped stones act as wedges, instantly blowing off the concrete's top corners. This edge cracking is known as spalling. The IS 6509 protocol dictates a strict repair. The defective edge must be cut back vertically by at least 50 millimeters, wetted with a neat cement paste, and repacked with a highly dry concrete mix to restore the sharp geometry of the gap. IS 6509 transforms random, catastrophic material failure into predictable, mathematically manageable behavior. It proves that the true strength of a continuous concrete pavement lies entirely in the mastery of its engineered weaknesses.